Hey everyone, and welcome to today's lesson about exponential functions. In today's lesson, we'll talk about the graph of exponential functions. We'll solve some real-world problems involving exponential functions, and then we'll look at the distinction between exponential and linear functions. So let's dive right in. An exponential function is a function of the form y equals a times b to the x. Again, that's y equals a times b to the power of x. Exponential functions, again, represent some form of repeated multiplication. When I look at the graphs of exponential functions, you can see the first example, when the b value is positive, the graph starts close to the x-axis and then quickly increases. Now, if I use that same b value but make it negative, the graph again starts close to the x-axis, however it becomes negative very, very quickly. You'll notice that these two graphs look very similar. In fact, they are a reflection over the x-axis. The similar can be said about a b value that's a fraction. It starts high and works its way back to the x-axis very, very quickly. If I take that same base and make it negative, now it starts low and it works its way up to the x-axis very quickly. Again, these graphs are reflections over the x-axis. We can use this idea when graphing some of the exponential functions down below. If we look at example number 1, we are given two exponential functions, and you can see that the base is the same, that b value is the same, but the a value is one's positive and one's negative. So our graphs will be reflected over the x-axis. In order to graph, we're going to go back to our trusty old table, and we're going to pick our favorite x values, -2, -1, 0, 1, and 2. I'm then going to plug in these x values and generate a y value. Once I've got x and y values, I can plot my points and then connect to make a nice graph. So if I plug in -2 for x, I end up with 0.056, and I'm rounding to the nearest thousandth. If I plug in -1, I'm left with 0.167. If I plug in 0, I get 0.5. If I plug in 1, I get 1.5. And if I plug in 2, I get 4.5. Let's head on over to the graph now. I'm over at -2, and 0.056 is just very, very tiny, so I'm going to be very close to the x-axis. At -1, I'm at 0.167, so just a bit higher. And then over at 0, I'm at 0.5, so midway between 0 and 1. At 1, I'm at 1.5, so I'm starting now to increase pretty quickly. So 1.5. And then at 2, I'm jumping up way up to 4.5. So you can see as those x values are increasing, the y values are going to increase more rapidly. So if I connect these points, it's very, very close to the x-axis, and then it's increasing quickly. And I have an arrow on both ends to show that that graph extends in both directions. Now, the only difference about the graph in part B is that it is reflected over the x-axis. So those points that were above the x-axis are now below, but in that same position. So when I'm over here at -2, now I'm down at -0.56. And when I'm at -1, it's -0.167. And so on. So over at 1, I'm at -1.5, and at 2, I'm at -4.5. So you can see I have this quickly descending function with arrows on both ends here to show they're continuing in both directions. I'm going to draw this graph on the same spot over here, and you can see that we're looking at a graph now reflected over the x-axis. Alright, let's move on to talking about some differences between linear functions and exponential functions. So if you remember that linear functions have a common difference, well, exponential functions, they have a common ratio. Easy way to think about this is that linear functions are when I'm adding and subtracting, and in exponential functions, I'm multiplying and dividing every time. All right, so you can see that there's a common ratio. If I do 4.5 divided by 1.5, and I do 1.5 divided by 0.5, I'm going to get the same number every time. As in a linear function, I would be adding or subtracting the same number every time. So let's take a look back at a few more examples. Example number 2, this is an application problem. It says an initial population of 20 rabbits triples every half year. Okay, and this half year is very important, every half year. The function f of x equals 20 times 3 to the x gives the population after x half year periods. How many rabbits will there be after 3 years? Well, 3 years equals 6 half years. So I'm actually going to plug in 6 to my function. So f of 6, 6 half years, times 20, equals 20 times 3 to the 6th power. I can go ahead and plug that in my calculator. I'm going to get 14,580 rabbits. That's a whole bunch of rabbits. All right, looking at example 3, I'm starting to look at that difference between whether it's a linear or an exponential function. And in part A, I'm going to look at the difference in the y values. If I have a common difference, I'm going to know that it's linear. And if I have a common ratio, then I'm going to know it's exponential. For me, it's easiest to start by checking to see if it has a common difference. If it doesn't, then I can move on to a common ratio. So if I look here from -1 to 1, that's a difference of 2. From 1 to 3, that's a difference of 2. And from 3 to 5, that's a difference of 2. So since I have this common difference, this is linear. Looking at part B, I've got a function that's y equals 3 times 6 to the x. That looks like y equals a times b to the x. Remember, an exponential function is any function of the form a times b to the x. This is an exponential. In example number 4, I'm looking at this same kind of idea, trying to decide whether the function is linear or exponential. And we're looking at these real-world situations and deciding which type of function would model that better. It says Jack pays $30 each month for a gym membership. So I'm constantly adding $30. It's $30 each month. Since it's that consistent number, this is a linear relationship. Linear relationship. I like to think of this as addition. I'm adding $30 every month. In part B, I've got a culture that starts with 1,200 bacteria. The number of bacteria in the culture is halved each day. Since it's being halved, I'm multiplying by 1/2. Or dividing by 2. Since I'm multiplying or dividing each time, this is an exponential function. Okay, since this one is dealing with addition and moving up by the same amount every time, this one I'm multiplying or dividing by the same amount each time. It is exponential. Example number 5, I've got a table that shows the amount of water in a bathtub at different times. Does the table represent a linear or an exponential function? Explain. What does the common difference or common ratio mean? So again, when I'm left with this table, I want to try to check for a common difference first, and if I don't have a common difference, I can move on to try to find a common ratio. So let's do 70 minus 49, and I get 21. 49 minus 28 is 21, and 28 minus 7 is 21. So my common difference is equal to 21. Therefore, it's a linear function. The question also asked, what does this common difference represent? Well, the table shows the amount of water in a bathtub over a period of time. So this tells me that 21 gallons per minute drained from the bathtub. I know that I'm draining from the bathtub because the numbers are decreasing. All right, let's go ahead and turn the page. And now you have an opportunity to try some questions. So please pause the video, try the self-quiz, part 1 and part 2, and then check your answers. All right, part 1 of the self-quiz, does the table represent exponential function? Yes, it does. I am multiplying by 3 each time. So my common ratio is 3. What is the graph of 7 times 2 to the x? I made a table for this, x and y, and used my 5 values. If I plug in -2, I get 7/4. If I plug in -1, I get 7/2. If I plug in 0, I get 7. Plug in 1, I get 14, and 2 is 28. So if I look at the graph here, it should have that exponential shape, and I'm not being very nice in plotting all those points, but your graph should have that general exponential shape where it's starting off close to the x-axis and then increasing rapidly. In question number 3, it asks about the species of insects that doubles every year, and I'm given this exponential function, and it asks me how many insects will there be after 4 years. So I am plugging in f of 4. So I have 2200 times 2 to the 4th power. Plug that into your calculator and you're left with 8,800 insects. The last part of the self-quiz, does the rule represent exponential or a linear function? This is linear. There are no exponents, which kind of gives it away. And you can see that constant difference, that common difference, is 19. Part 2 says, can you model the situation by a linear function or an exponential function? Explain. And the situation is that Lisa saves $10 each day to buy a bike. So if you look at the amount of money that she has, it's going to be increasing by 10 each day. That represents a linear function. It's got a common difference of 10. Pardon my sloppy handwriting there, I'm trying to write too fast. And for question number 3, it says, which function increases faster over the interval from 2 to 5? And I'm given 2 functions. P of x here is linear, and R of x is exponential. I know that exponential functions increase quicker than linear functions, so R of x will increase quicker. I hope you guys learned a whole lot today about exponential functions and can determine the difference between exponential and linear functions. If you have questions, please come to class ready to ask. That's all for now.